Hello again. So today we're going to look at our learning objective number 8 from lecture 15. We're going to be looking at the radial probability function graphs for atomic orbitals. So when we solve for our Schrodinger equation and we take its square, we square it, we find these orbital representations or the probability densities. And those probability densities are what give us that visual representation that we call orbitals. So what we looked at in the last video. So a electron density model would look something like this right here. So this is what would happen if you solve for the Schrodinger equations and then squared it. You would get a bunch of dots on an XYZ plane. And then that represents the probability of finding an electron. If that electron had a specific set of characteristics. For instance, because we're in this visualization, we are talking about a 1s orbital. We would be talking about an electron in a 1s orbital. It would be a spherical shape where it is very, very close to the nucleus. So the point where all of the axes meet is our nucleus. So looking at it as a probability versus distance from the nucleus, you can see that most of the electron density is right by that nucleus, but it goes to 0 at the nucleus because there are no electrons at the actual nucleus. So there would be no nodes, so no nodes, if we have a 1s orbital. Once we go from a 1s to a 2s orbital, we produce a node. And so here's our node list. We can see that node here on this slice of the orbitals. So it's a sphere, and right in between the 1s, almost looks like a little heart, in between the 1s and the 2s, there's a node of no electron density right there. Okay, then if we look at a 3s, so if we look at the Schrodinger equation for a 3s, we have 3 nodes associated with them. And again, we could see those nodes in their little heart shapes right there. So as we increase our n value, we increase our nodes. So for our s orbital or subshell, as we increase our n value, we increase our nodes. And those nodes are our points of 0 electron density. Okay, so thinking back to our wave, when that wave hits the axes, that's kind of like our node right there. Okay, now to determine these right here, these are called radial nodes. To determine our number of radial nodes for any type of orbital, you use the equation radial nodes are equal to n minus 1, or sorry, minus L minus 1. So whatever your n value is, you minus your L value, and then you minus 1. So for instance, if we have 1s, the n is equal to 1, the L is equal to 0. So you do your radial nodes equal to 1 minus 0 minus 1, which gives you 0 nodes. Okay, now when we go from a s orbital to a p orbital, Remember, our p orbital looks something like a dumbbell, so there is already a node right there. So that is a point of no electron density. So with an L equals 1, we have what's called an angular node, which is generally between lobes. That angular lobe node is equal to our L value. So because our L equals 1, our angular nodes are equal to 1. To determine our total number of nodes, we can either add together our radial node plus our angular node, or we can say that our total number of nodes is equal to n minus 1. So whatever your n value is, minus 1 from it, and that'll give you your number of total nodes for any n value. Okay. Moving on to our d and f orbitals. Here we have L equals 2 and L equals 3. So for each of them, we have our angular nodes. So we have 2 angular nodes for our n equals 2, or our d subshell. And we have 3 angular nodes for our f orbitals. And we can see those. We look here. All right, so there is an angular node here and here for D, and then for F, one here, here, and here. So each of them are going to have angular nodes. And as we get further and further from the nucleus, we are going to form more and more of our radial nodes as well. So if we have, let's take our p orbital, if we have a 2p orbital, our radial nodes would be equal to 2 minus our L value of 1 minus 1, which gives us 0. But if we have a 3p, we're going to take our 3 minus our L value, in this case 1, minus 1, so that gives us a 1 radial node as well. Okay, that's everything for our look at radial distributions and electron densities of our different orbitals. Nice, short, quick one. Thanks. Bye, y'all.